Every heartbeat begins with a tiny signal that keeps the heart in rhythm. But for patients with arrhythmia, these signals become very irregular, too fast, or way too slow, and this can lead to dangerous heart conditions. To solve this problem, we as engineers have designed a specific device, a cardiac pacemaker, which sends pulses to the heart. But the pacemaker listens to the heart's natural rhythm and compares it to the ideal desired rhythm, and then only sends signals when the heart strays from this ideal value. So what the pacemaker does is basically a feedback control system where it compares the heart's output and alters its input to ensure that we have the desired rhythm from the heart. To represent this mathematically in electrical circuits, we use the transfer functions and our forward loop functions to simulate what the heart does in nature. So once we are able to obtain our transfer functions, it helps us to determine how stable our system is or how unstable it is, how fast it takes the system to correct itself when it strays from a desired output.
Imagine pressing the button of an elevator taking you to the fifth floor. So basically, you would expect this elevator to move smoothly, take you there quickly, and then when it reaches there, it should stop without shaking. So behind this simple action is a control system that's constantly adjusting the behavior of the machine to ensure that the response is fast, accurate, and stable. In the world of engineering, we analyze systems like these by analyzing the factors and parameters that affect the response of the system to an input. One of such important parameters is the damping ratio. The damping ratio determines whether the system settles smoothly or oscillates a bit before settling. In this presentation, we'll be talking about a feedback control system, and it will be determining the parameter A, which is required to produce a desired damping ratio of 0.5. We move forward to talking about two important parameters as well, the rise time and the maximum overshoot. So the rise time will determine how quickly the system reaches its targets, and then the maximum overshoot determines how much the system exceeds its final steady state.
And we have our forward transfer function and the feedback transfer function here. And we are to determine the rise time and the max overshoot. We already have our damping ratio to be 0.5. So starting, we have our closed loop transfer function formula here. This will help us to analyze how we will find our rise time and the maximum overshoot. So substituting the GS and the HS into the closed loop transfer function to analyze the control system, we have the GS to be 16 all over S into bracket S plus 0.8. This is the numerator, and the denominator is 1 plus the GS and the HS. So doing some small algebra here or some small analysis here, we have our final answer to be 16 all over S squared plus 0.8S plus 16 plus 16AS. So you group like terms. So you group according to the exponent. So we have our S exponent 2 here plus 0.8 plus 16A, or also group as S plus 16.
So in order to find our natural frequency, we compare the standard equation with the characteristic equation. So we identify the natural frequency, which is omega square and equal to 16. So we take a square root of both sides, which is 16 square roots. So the natural frequency will become 4 rad per second. So from the compared equations, we see that 2 zeta omega n is equal to 0.8 plus 16. So initially, we had been given that zeta is equal to 0.5. And we found out that omega n is equal to 4. Yeah, the natural frequency is equal to 4. So substituting into the equation, you have 2 times 0.5 times 4. 0.8 plus 16. So we have 2 times 0.5 giving 1 times 4, because 0.8 plus 16. Then we put that times. We have 4 minus 0.8 because 16. 0.2. So that's the value of A by comparing the two equations and substituting the damping ratio and the natural frequency. Calculated parameters. We move on to find the rise time. Rise time is basically the time the system takes to reach its first peak response. So substituting the values of natural frequency omega n equals 4, then the damping ratio 0.5. We have the rise time equals I minus tan inverse bracket will be square root of 1 minus 0.5 squared all divided by 0.5 as of the whole expression divided by omega n as 4 square root of 1 minus 0.5 squared. So it's called calculating this gives us rise time equals 0.605 seconds. This indicates that the whole system takes a time of 0.605 seconds before reaching its first peak time response.
Forward, we'll be calculating the maximum overshoot of our system. And to calculate the maximum overshoot, we only need the value of zeta, which is our damping ratio, the value of 0.5. So we have our equation here, that's the equation for a standard second order equation, of which our equation is. So we have the value of zeta to be 0.5, and then we substitute it into our equation. So we have our maximum overshoot to be equal to E or negative 0.5 pi, all on the square root of 1 minus 0.5 square multiplied by 100. Since our maximum overshoot is being measured in the percentage, calculating this will get a value of 16.3%. And this indicates that our system rises above the final steady state with a percentage of 16.3%. So instead of 100%, it oscillates at a total of 116.3% before settling to the 100%, which is our final steady state.
In conclusion, we analyze the feedback control system by analyzing the rise time and maximum overshoot. So we found the rise time to be 0.605 seconds and maximum overshoot to be 16.3%. So this result indicates that the system responds quickly whilst maintaining a moderate level of overshoot. And also, the damping ratio of 0.5 shows that the system is underdamped but stable, which explains the overshoot and oscillation of the system before settling.
The circuit analyzes a second order system and determines parameters like the damping ratio, the rise time, and the maximum overshoot. Biomedical devices are control systems that must respond quickly, adequately, and safely. Some applications of the biomedical systems in control systems include prosthetic limb control system. The rise time determines how the joint reacts with movement. When the overshoot is too much, it causes jerky movement. The damping ratio provides a smooth and natural response. Another is the cardiac and ECG monitoring system. So the rise time determines how quickly the system reacts to sudden heart rate rhythm. And the overshoot causes a distortion in the signal.
I'm Samuel and I'll be interviewing my peers on what they've learned so far in our video assignment. So Francisca, in simple terms, how do you explain how damping ratio affects the behavior of systems?
It determines whether the system will overshoot or return to stability.
Okay, so Vanessa, can you think of any biomedical device where you think controlling overshoot will be very important?
An insulin pump.
Okay, that's a very good answer. Can you explain your answer?
An insulin pump is used to deliver insulin to regulate blood sugar. So if the system overshoots too much, it delivers too much insulin, which causes low blood sugar. That's why engineers design systems to control overshoots.
Thank you. Okay, so Alexandra, what is the most important concept you learned from example 2.4?
The Okay, well, so the most important concept that I learned from our assignment given was that the system's parameters directly affect the control system and its behavior. For instance, with the question given, we compared the standard equation to the characteristic second order equation, and with this we were able to determine the specific parameters that give us our desired damping ratio. With this, engineers are able to adjust certain system parameters to help us find performative characteristics like rise time, overshoot, and damping ratio. Thank you.